Alright, silly people, here's the situation. We have this girthy time-dependent wave function, and we're meant to prove that it satisfies the time-dependent Schrodinger equation, and then we need to find the square modulus of it, and then we also need to prove that it satisfies Iron Fist's theorem. So let's kind of just get into it then. It's going to be sort of a left-hand, right-hand proof, so I'm going to do the time derivative of this first and multiply it by IH bar. So we kind of get the m omega over pi h bar stuff, but with an IH bar as well. And then in these brackets, I'm going to put the derivative of all the stuff in the exponent with respect to time. So it's going to be minus m omega over 2h bar times x naught squared over 2 times minus 2i omega times e to the minus 2i omega t plus I h bar over m, or plus 2i omega x naught x e to the minus I omega t. And then that's multiplied by the stuff in the exponent uh, that we don't really care about anymore. So first of all, let's move the m omega over 2h bar stuff into the parentheses. So we just get, this is going to be, so this 2 cancels out this 2, so it's minus. So when we put the minus sign on it, it's plus m omega squared times x naught squared all over 2h bar e to the minus 2i omega t. Actually, it's supposed to be an I here as well. And then here we've got the m, no m anymore, the m's cancel out. We have h bar omega, we don't even have h bar anymore, minus I omega over 2. I think that's it. Yeah. And then plus, actually this one is minus now, m omega squared I x naught x e to the minus I omega t over h bar. Fun stuff there. And then it's also multiplied by the exponent, which we still don't care about. It's blah, blah, blah. Now we can move the IH bar in there. So now this is minus m omega squared x naught squared over 2 e to the minus 2 I omega t plus h bar omega over 2 plus m omega squared x naught x e to the minus I omega t. Pretty cool stuff there. And also still times the exponent term. It's this big one up here. Now let's do the right hand side of the equation, where we have to take a second derivative of the wave function. So let's get the first derivative. That's m omega over pi h bar to the 1/4. In these brackets, I'm going to put the derivative of the argument of the exponent with respect to x, which is going to be minus m omega over 2h bar 2x minus 2x naught e to the minus I omega t, right? Those are the only things which depend on x. And then it gets multiplied by the girthy exponent. Taking the second derivative then, we still have this guy. We have a term proportional to the first derivative of the argument, so that's going to be minus m omega over h bar x minus 2x, or no, it's just x minus x naught, e to the minus I omega t. And you square all of that, and there's also going to be a term which is just proportional to the derivative of this stuff here. So minus m omega over h bar, and then all times the big girthy exponent. So let's start constructing the full right-hand side. So it's minus h bar squared over 2m times the second derivative plus m omega squared x squared over 2 times the wave function. So we've got a bunch of stuff which depends on m omega over pi h bar to the 1/4. A bunch of stuff. And then we have minus h bar squared over 2m times all this shit. So minus m omega over h bar x minus x naught e to the minus I omega t. I know I'm getting crazy with the derivatives or the parentheses, but just believe me. And then also m omega squared x squared times the wave function. So I'm just going to write this as plus m omega squared x squared over 2 times all of that times this junk. Right. We can simplify this by quite a lot. First of all, by actually doing that square. So we have minus h bar squared over 2m times m squared omega squared over h bar squared x minus x naught e to the minus I omega t squared minus m omega over h bar plus m omega squared x squared over 2 we can expand this square now and start moving the constants here into there. So now we're going to have the h bar squareds will cancel out. We'll have m omega squared minus m omega squared over 2 times x squared minus 2x x naught e to the minus I omega t plus e to the minus 2 I omega t minus m omega or actually this is going to change to just h bar omega over 2 with a plus sign because there's a minus sign on that. And that's still plus m omega squared x squared over 2 times the stupid exponent. Now this is really starting to look familiar because now we have minus m omega squared x squared over 2 plus m omega squared x naught e to the minus I omega t minus m omega squared over 2, and there's supposed to be an x naught squared here. I just realized this is x naught squared over 2 e to the minus 2 I omega t plus h bar omega over 2 plus m omega squared x squared over 2. Right. And then, interestingly enough, this m omega squared over x squared over 2 cancels out the other one. And then we compare to what we got originally for the left-hand side of the time-dependent Schrodinger equation, which was this junk here, or times the exponent of the crazy stuff. But yeah, you get the picture. Yeah, these two equations are the same. Look, we got the same minus sign here as here. That's cool. We got this term and this term match up. This term and this term match up. So we are okie dokie there. So let's now move on to finding the square modulus of the wave function. But instead of doing that immediately, I'm going to rewrite the wave function given in the problem in a way that is going to be easier to work with, given the context of squaring it. Just separating anything that depends on I from the rest. So putting all the real stuff in one exponent. It's here x squared plus x naught squared over 2. And then anything that's imaginary or complex is going to go over here in the complex zone. And it's m omega x naught squared over 4 h bar e to the minus 2 I omega t minus I omega t over 2 plus m omega over h bar x naught x e to the minus I omega t. Right, that's just a little rewriting of the wave function. So, taking the square modulus then, that 1/4 will change to a 1/2. So we get the square root of this thing. We have that this exponent will be squared, so this 2 that was on the bottom of this fraction is going to go away. That's all that's happening there. And now this exponent has a bunch of crazy terms. So minus m omega x naught squared over 4 h bar, right? But then you have e to the minus 2I omega t plus e to the positive 2I omega t, because we're taking the square modulus. And then this term here will also get canceled out whenever you take the square modulus, but then we'll have a couple of terms dependent on x naught times x. And let me move it down here because I need a little bit more room. But it is just e to the minus I omega t plus e to the I omega t. So those look like cosine functions to me. I'll remind you the definition of the cosine function. It's cosine of z equals e to the iz plus e to the minus iz over 2. So then let's just rewrite a bunch of this stuff as cosines and sines, right? And also gonna go ahead and start simplifying this real exponent, because it's minus m omega x squared over h bar minus m omega x naught squared over 2h bar. And then in the other exponent, now I have minus m omega x naught squared. Multiply it by 2 to change it into the cosine of 2 omega t, and then multiply this by 2 as well to get cosine omega t. There's an x here. Cool. Now let's put everything in one exponent, and I'm going to factor out everything that is just m omega over h bar. So we'll have an exponent minus m omega over h bar, and then we have just x squared plus m omega x naught squared over h bar cosine 2 omega t plus 1 over 2, right? Plus, and that's not even true. This got factored out. It's just the x naught squared is what sticks around. X naught squared plus just 2x x naught cosine omega t. There's a reason I wrote it like that. That's actually a trig identity for cosine squared omega t. So we'll rewrite it like that. Pi h bar exp minus m omega over h bar x squared plus x naught squared cosine squared omega t plus 2x x naught cosine omega t. And then you realize that that is just the square of some factor that looks like just x plus, or x minus x naught, yeah, because there's actually supposed to be, I think this is going back a little bit, but yeah, when we factored out the minus m omega over h bar stuff, this is supposed to change to a minus sign. So there's a minus sign here. So this is x minus x naught cosine omega t squared. And you can leave it like that. So that's pretty cool. Now we can start looking at the expectation values of x, p, and potential. That's going to give us what Ironfest theorem is. So first we need the expectation value of x, which is just going to be the integral over all space of x times the mod squared, which we just got. So we have square root m omega over pi h bar, integral from minus infinity to infinity of x times this crazy term exp minus m omega over h bar x minus x naught cosine omega t squared. All right. We'll do a u substitution to make this integral sufferable. We'll do u equals x minus x naught cosine omega t, which does mean that du is equal to dx, so we don't need to change the differentials that much. But we do need to change what x is, because now it's looking more like u plus x naught cosine omega t these days. But now this exponent is way easy to write, just minus m omega u squared over h bar du. So any old integral that happens to be u times e to the minus u squared du is 0. That's an odd Gaussian integral. But we get to keep the other term. So we get the root m omega over pi h bar thing times x naught cosine omega t. And then the result of that integral is just root pi h bar over m omega, which means the radicals exactly cancel out. So this is just x naught cosine omega t. Yeah, so I don't think I mentioned what the particle's motion is looking like. You kind of need to. So if you look back at what we got for mod x squared, it becomes really like evident that you have what is pretty much a regular Gaussian distribution, but the center is moving back and forth cosine sinusoidally, with a frequency omega, right? Yeah, that's the only thing that's changing. It's like a Gaussian, but its center is moving back and forth like this with a frequency omega. That's all that's happening. And so we can look at now the expectation value of momentum, which is a little bit cursed because it's minus IH bar integral over all space psi star del psi del x dx. But we already happen to calculate del psi del x, so it's not that much of a problem for us. So we'll have minus IH bar times m omega over pi h bar to the 1/4, haha, to the 1/4 integral, and then also, I think there's another term which doesn't, yeah. There's another term that we can pull out of the derivative before putting it all behind the integration. It's just the m omega over h bar that we got from the first derivative. But now this is the integral psi star x minus x naught e to the minus I omega t times the big annoying exponent, which I have never written once in this video. And then we can use this like crazy normalization factor to move it over here by the exponent, and then it just becomes psi again. So we have minus, also whenever we did the derivative, we inherited a minus sign from the first derivative. So this changes to a plus. So this is in fact just m omega times I times the integral x minus x naught, and then e to the minus I omega t times mod squared psi dx. Funny stuff. We'll just expand the definition of the mod squared now. So we have the m omega over pi h bar here again. We still have this integral psi, or we have the integral now x minus x naught e to the, I still cannot write this correctly, e to the minus I omega t times the exponent minus m omega over h bar x minus x naught cosine omega t squared. And that h bar did not go well. So we're going to make another u substitution, right? It's going to be the same u substitution. It's still just u equals x minus x naught cosine omega t. So du is still just dx, so we don't need to change the differentials. It's this term which is interesting to deal with, right? So comparing it to u, it's going to be u plus x naught cosine theta, or cosine omega t, minus x naught e to the minus I omega t. Whoops. Yeah, that sort of thing. And so we can expand the definition of cosine, actually. That'll help turn this around. So this is going to be x naught over 2 e to the I omega t plus e to the minus I omega t minus x naught e to the minus I omega t. And then we can move the term which is the negative exponent in here, and now we have e to the I omega t minus e to the minus I omega t. That's pretty cool, and that's the least cringe way we can write it right now. So let's keep going into the integral. Just using that, we now have I m omega square root m omega over pi h bar times the integral from minus infinity to infinity of u plus x naught over 2 times e to the I omega t minus e to the minus I omega t times the e to the minus m omega over h bar times u squared du. Again, the odd Gaussian term does not contribute, but the other term does. So we'll have a I m omega, and let's actually write it in a pretty special way. We'll write it in a minus m omega times m omega over pi h bar. This is going to be x naught over nothing. Let's just write x naught here. And this is e to the I omega t minus e to the minus I omega t over I. All I did there was I switched around like the sign of the thing by putting the I on the bottom of the fraction. So yeah. And there's also a 2 here. And then the result of the integral is pi h bar over m omega. So the radicals cancel out again. And this is actually just the definition of sine omega t. That's why I wrote it that way. So we get minus m omega x naught sine omega t. We can check Iron-Fest's theorem handily now, because remember, that's the result we got for the expectation value of p, which should in theory be m times dx dt, right? So it's m times d dt of cosine, or x naught cosine omega t. That's what we found for the expectation value of x. So it's m omega minus m omega x naught sine omega t. That is true. But Griffiths does ask us to do a pretty specific form of Iron-Fest's theorem. That is that the expectation value of the force is equal to the change in momentum with respect to time. So we know what the potential is. It's just m omega squared x squared over 2, right? So we have minus del x times m omega squared x squared over 2 equals d dt of minus m omega x naught sine omega t. And then we have that this is minus just m omega squared x equals just minus m omega x naught times, or it's omega squared x naught, my bad, cosine omega t. If you plug in the expectation value of x for x on the left-hand side, we get minus m omega squared x naught cosine omega t, which is the same as the right-hand side. So, pretty good. That's it.